Okay, now recording. Okay, so what does it mean? Should I start all over again?
Yes, sir. Yes, sir.
Oh,
Let's
yeah.
continue.
You can start over again, sir.
Okay. So topology is really about relationship between geographic features. The word feature is said to say an object, so don't be scared. But in geography, when we say a feature, then everything that makes up, your environment, the things around you on the surface of the earth, they are all features. You can have what we call linear features, point features, aerial features. So, for example, the sea is an aerial feature. It covers a large expanse. Are you with me? But we can establish that the whole concept of topology is about relationship between geographic features. So every object, where, like someone said, where your nose ends is where someone's whatever begins. Are you with me? Like, there is a relationship between objects in the world, on the earth. Are you okay? So we can look at, like, the typical example I gave was the T junction. Is all right. So in the T junction, there's a relationship between the road that's coming to join the main road. So that's a relationship there. Please, if you don't get this one, then that's it. You are done. Okay. Very simple concept. Two roads joining. One is actually going straight up. There's one that's actually coming to turn left or right. There is a relationship right there at that junction. That's why junctions are so important. There's a relationship going on. Are you with us? All right. So in GIS, if you remember, GIS is about computers, it's about software, it's about data. So please don't think about how the computer and software is going to implement this relationship so that we will know that we have reached a junction and we need to turn the left. All right. So topology practically is how I've explained it to you. But by definition, topology is referred to as the spatial relationship between geographic features. End of story. So topology refers to spatial relationship or geographical relationship between geographic features. Okay, or we can swap it. Geographical relationship between spatial features. Spatial relationship between geographic features. I told you that spatial and geographic are words that can be used interchangeably. They mean the same thing. Are you okay? So this course could have been called Spatial Information Systems. Are you good? Are you happy? Okay, so now it describes the relationship between connecting or adjacent coverage features. Like I said, when we look at this diagram down here, then we can actually see that there's a relationship. You haven't actually fought over land before. You appreciate what I'm talking about. That the area B and the area C share a common boundary. That is a relationship there. And that is what has caused people to actually fight over years, to go to war. Are you with me? Relationship. Is that not the case with even like relationship between two partners? Are you okay? That there's always some kind of conflict. So topology is there to solve that. In other words, what we do in GIS is that we use a software to actually remove topological errors by setting topological rules. Are you okay? So topological rules are actually based on concepts, are you okay, of GIS. So one concept of GIS topology, and then there are three basic components of topology. Is that okay? What are they? Connectivity rule, area definition, and contiguity. Very, very simple ideas. Connectivity rule is actually saying that lines can join at nodes, are you okay? And every line has vertices, and the beginning of a line is called a node, are you okay? And the end is called, the other end is also a node, are you okay? And you can only join two lines at nodes. Like this is like a typical, connectivity rule. So let's look at it properly. Okay, so connectivity. All right, connectivity. So the first rule of connectivity here is that points along an arc that define the shape are called vertices. So someone will be asking, so what? Are you okay? But then it's very important for you to know that if you're actually looking at a typical CAD drawing, for example, as an engineer at level 400, you appreciate that when the line is actually a curve, then you begin to see these blue dots, are you okay, that go in between. Are you okay? That kind of seem to define that the line is curving. Are you okay? Now, so instead of just saying a line, we are using the word arc. Are you right? So that's the line is arcing. It's bending. Are you with me? All right, so in connectivity, then we are saying that those points that are helping us to define the arc, are you okay? The points along it are called vertices. It's a rule. There are no questions. Are you okay? All right. No hold up. Next one is that the endpoints of the arc are called nodes. Take note of that. Why? By knowing that they are called nodes, the third rule says that arcs join only at the nodes. So if you actually look closely at these rules, you realize that this is all we need for us to simulate a certain network. Talk about train network, complex train network. We're not talking about Ghana Railway Authority here. We're talking about serious rail networks, multi-hierarchy type of network, road network. Are you okay? In that case, they realize that we need to have, a digital system, a system that kind of helps us to track when is this train going to arrive here, when should that other train move on. Another example in transportation. So I'm gradually introducing the concepts, the application. Are you getting that? So try and follow it, even though the notes doesn't really mention it. Yes. So here, typically that's a route. And then these are nodes, the round ones, and the bigger ones. And then of course, between every node, you have vertices in between this one and that. Are you okay? So the routes or the routes, Americans like using that word route. And then the beginning and the end points are actually, shown as the blue dots. Okay? All right, so we're done with connectivity. And if you want to ask a question, like I said, you can ask. If you don't really follow, if you what is he talking about? I can always go over it. Let's move on. Area definition is just like what we talked about. Okay, yeah, you have areas, and then you want to find out, what the relationships are between the different areas. So we said that an enclosed polygon, the first rule in area definition or containment, okay, which is also known as polygon arc topology, is an enclosed polygon has a measurable area. So when you take a polygon, what makes a polygon is that the polygon you can measure the area of a polygon, but you can't measure the area of a line. You can't measure the area of a point. So the first thing to accept as a rule in the area definition or containment concept in topology is actually the fact that a polygon we should be able to measure its area. Are you okay? Now, the second one says the list of arcs that define the boundaries, closed areas are maintained. So in other words, every polygon is actually made up of lines or arcs. Like I told you, the arc is like a line, but then we are assuming that not all lines are straight. So we are using the word arc. So list of arcs define the boundaries, and then closed areas are maintained. All right. Also, polygons are represented as a series of coordinates that connect to define an area. Of course, but we realize that coordinates defined are the basic, are you okay? Right? They are the fundamental primitive of everything that we are doing. Are you okay? Line, every object has to, can be broken down to points. Are you okay? So now when you look at this table here, you can see that polygon B is actually made up of arcs 1, 6, 8, and 5. So polygon B is bounded by this arc 1, then 5, this short one here, 8 going all the way, 6 up to this point. Is that okay? And then so 1, 6, 8, and 5. Same for C, E, F, D. So like if you got the idea of the B, you can apply it to the rest and you'll be okay. E is an interesting one, okay? Just one straight and closing arc. So that one is an interesting one. All right, let's take note of that. But then this is how the computer will represent polygons. That's what a series of coordinates. Is that okay? A series of coordinates. All right. So let's move on. The last one, but very interesting, is contiguity. Not continuity. Is that okay? Contiguity. So I mean, it's not a spelling mistake. That is what it is. It's okay. Contiguity. The rule says that every arc has a direction. So here we're talking about flow. Are you okay? Where is the water flowing from? Which you know, where two rivers meet, what do we call that? Yeah, where's this water coming from? Where's it going? Are you all right? So we need to keep track of direction, especially in network. So topology is really very much applicable to network analysis. Are you with me? All right. GIS maintains a list of polygons on the left and the right side of each arc. Here, the analogy is when you sleep. Yeah, there's an analogy. When you sleep and you wake up in the night and you want to know where the light switch is, because you wake up, not many people sleep in one orientation and wake up in another orientation because they are actually like struggling in bed, struggling to sleep. Yeah. So you realize that there's something that you do to find out where the switch is on the wall. I.e., you look around, you start touching things, you start touching, and you ask yourself, where is the fan? If the fan is on my left, it means my switch has got to be on my right. Yeah, I don't know if anybody in this class can really tell you, but for me, I feel it happens a lot, especially when there's a lot of, blackouts in Ghana, and I don't know about Nigeria. I hear Nigeria's situation is better. I won't go there. Okay, I won't go there. But obviously, yes, contiguity allows the computer to determine where things are moving, what direction. How do we tell, okay, this is a one-way street. So if I'm working out the shortest route, then I shouldn't be using that, or how should I even incorporate that route or that road into my analysis? The computer actually does this interesting thing that we do every day when we go to bed. It keeps track of what polygon is to my left, which one is to my right, and then it's able to tell that, okay, you are going left or you are going south or west or east. So here, typically, if you look at this diagram, it explains it. Okay, that if I'm moving along arc number 10, then to my left, the polygon is D, and to my right, I have the polygon F. See that F seems to be an area that is shared by most of the polygons here. Are you all right? So this is how the computer is able to figure out that you are actually moving in a certain direction. Otherwise, how would it know? Okay, so that is topology for you. So here you see left right topology, and it's a table. Okay, everything that we see here is a graphic. The computer stores it in a structure like this, looking more like a table. So let's take note of that. So that brings us to the end of the three concepts in topology. Is that okay? The three, virtually like the three concepts have rules. Are you okay? All right, so what are they? Containment or area definition, connectivity or arc node topology, and then contiguity. Is that okay? Which actually helps us to appreciate and to establish a relationship between objects within the space around us or the project area. All right. So let's move on, talk about another topic. Unless someone want to ask something, I mean, I'll just talk about that course. So I think this will be the last one in terms of, concepts, but there are more anyway. Yeah, for now, this is enough. This is enough. Yeah. So the concept of layers should be easy for all of us to grasp because most of you have used AutoCAD at a point, maybe level 200 or level 300. But I'm sure by that time you should have used some AutoCAD. And so you appreciate that in AutoCAD we have layers, and the same thing applies to GIS. And layers are simply layers. You overlay layers, you put one thing on top of the other, you have done an overlay. Are you okay? All right. And in GIS, the magic thing, okay, that actually allows the different layers to be, piled up is the coordinate or the geographical location, the longitude and the latitude. So as you can see, it's like as if we are actually piercing through the five different layers. Five different layers. Are you okay? 5. Yeah. Okay, we are actually piercing through all that along a particular coordinate. In other words, at a particular location, there are about 1,001 things that are happening there at any particular point in time. I don't know if you heard about or you actually watched the movie in which a town was actually sitting on a gold, reserve, the resource, a very huge gold resource, and then they had to, they were thinking the decision was being made whether they should be, the whole town should evacuate because there's gold under the town, so you people need to move, and they thought that they had a history, a connection with the place, and it became a whole lot of kind of hassle. But that is what it is, that at a particular location, you can associate a district with it, you can associate even a country with it, you can associate a temperature with that location, you can associate a soil type with that location, you can associate a geology with the location, you can associate a height with that location, you can associate, in fact, I'm saying all this on purpose so that you understand that the idea of what layers is. That okay? All right, so this is it. You have different layers, you can overlay them, but you see, when we bring it into the computer, the different layers will have to be in the same coordinate system. We will talk about coordinate system. We will talk about it. I don't know, maybe next week, I don't know, but soon. The next 4 lectures are to explain concepts to you. Next 4 few lectures ahead of us, you have to understand. That is all. And then we'll use a software. If you don't even understand what I'm talking about, when we use software, maybe you get it even more. All right, so that is the idea of layers, and the idea of having layers also affords us the opportunity to combine the layers. Are you okay? We can actually cut some of the layer, we can join some of the layers. Are you okay? And then when we do that, we want to actually call the map overlay. Are you okay? Map overlay, but actually we could just call it overlay. Are you okay? All right. So as we're saying over here, the combination of several spatial data sets, whether they are point data sets, line data sets, polygonal data sets, they create a new output vector data set in the overlay. So overlaying 2 data sets, we can carry out an operation. In other words, we can carry out an overlay operation that will actually join the 2 layers or find out between the 2 layers certain interesting aspects of it. So the first one in terms of overlay is what we call the union overlay. It's just like set theory, hierarchy, A union B. That's what it is. Combines the inputs. Sorry about the grammar there, but it combines the inputs and then we get a single new output. But yeah, so don't mind the grammar. It's okay. All right. Combine the inputs to get a new single output. Then we have the intersect overlay, which actually finds the inputs, the overlap between the 2 inputs. So A intersection B, that's what you're looking at there. Are you okay? Then we have what we call the symmetric difference overlay, which actually finds the intersection and says, no, I don't want that. So it's like A intersection B complements. So if you never understood set theory, I think this afternoon you're not very happy at all. Are you okay? But then that is this, if you want to really understand union intersect symmetric difference, then you have to use that analogy. It helps. So symmetric difference, it keeps the area of both inputs except for the overlapping area. Okay, so the overlapping area is the intersection area. Are you with me? All right, so let's look at typical projects in which we are trying to dig through an area. Are you okay? It's like a pipeline project going through here, but then there are different concessions and interests which are even overlapping, and we want to find out which parts, how are we going to be affected, which parts of the project do get affected. Are you okay? So what we've done over here is to just do some kind of intersect. Are you okay? We put the layers together and we find the intersection. Are you okay? Which area is common to the pipeline project and the concessions, which is this class. Are you all right? So if you actually find yourself within that blue area, highlighted, cyan highlighted area, then you know that you have to, take interest or whatever you have to do. Are you okay? All right. So union overlay will combine this layer and that layer, and we get that. So it's like I see these lines you are seeing here now appear here. Are you okay? Simple as that. It's data set. Symmetric difference is saying that, okay, you found the intersection is A, that's fine, thank you. But we don't want that A. We want anything outside the A. That is symmetric difference. So it's like as if we obtain a cookie cutter. Are you okay? It's like a cookie cutter. The symmetric difference, which is like that overlay, we end up having what, areas that are without the intersection area. Are you okay? All right, so that is overlay operations for you. So we can actually do some clipping. Are you okay? Data extraction and all that can be done, okay, in GIS. Are you okay? You can just clip, we can mask an area. So I can actually take all the, the road networks in Ghana and give it to you. But then your project area is around the Accra area. It's okay. You have the whole Ghana, all the routes as a data set. But then we can actually clip or mask it so that we just get the routes within Accra. We don't need to present all the routes in, everywhere. We don't need that. Okay. So in that case, that is where overlay becomes very relevant. Now, when I'm talking about map, algebra, and raster analysis here, but please just leave it for now. Okay, because that will start telling me one. Okay. I need to talk about raster and then vector data model. It will come out. Is that okay? As we need it. All right. So this would be probably the last topic for today. Looking at the time, I haven't even checked the time, but I'm suspecting that we have maybe 20 minutes. I'm not sure. Yes.
Yes, sir. Yes. We have about 20 minutes.
Yes, yes. So let's talk about buffer operations. And buffer operations are all about leaving a certain, gap, a certain area. Are you okay? Reserving it. That's what we all know. So if there's war in an area, the UN always create a buffer. Are you okay? That is how they solve most of these peacekeeping play. That's what they do. They create an area. They say this warring faction, you cannot, all of you cannot. I think it happened in Ivory Coast. They had they had some, issues there, and the UN, when they created a buffer between the north and the south. Are you okay? God forbid, you don't want war, but I'm just using that to explain to you how it works. Let's talk about, if you want to understand buffer operations, think about fire belts in the farms. When it's dry season and the fire is gutting areas and you're not sure when your farm will get gutted, one of the things that you're advised to do, we have 10 minutes, is to actually create a belt around your farm. That is buffer. That space that you leave around the object is called a buffer. Are you okay? Sometimes also called buffer zone. Are you okay? All right. So now, what is buffering? So after everything I've said, now the theory should make sense. Buffering is used to constrain the space around individual land features or individual features. So in other words, I take the object and then I constrain. So it's a mathematical operation. Think about it. If it's a location that I'm actually constraining space around, then I'm getting a circle. This one is math. Honestly, if you go back in secondary school, this was there. Are you okay? But then here we really talking about it in a very practical and interesting way. It is generally used for defining all the spaces within a certain distance of a type of feature. So you can take a road and create a buffer around it. Are you okay? And so you can also take a farm and create a buffer around it. You can take your house. Okay, I live here. Okay, let's constrain space around that. All right. So this is a question I always throw it to the class. All of you think about it for a moment. If you create space around a point, what shape would we have? Anybody can unmute their mic and give me an answer. When it comes,
you said a point.
yes.
So you have a circle.
You get a circle. Thank you very much. Okay, when you have a line, what about a line? How would you get? Just say
So
it.
you get a rectangle.
Okay, yeah, it depends on the line, isn't it?
Line, yeah.
So everywhere that the line is going, if it's actually kind of bending, then of course the actual area that is constrained, the buffer region is also like that. The thing with the line is that instead of getting a rectangle, we can get a polygon. We can call it a polygon because sometimes the end of the line, we don't cap it
As
with a square. Okay, we can cap it with a semicircle. In that case, that will be a rectangle. That will be, we just call it a polygon. All right. So when you actually constrain space around your farm, let me ask you again, do you have which area? Say again, let me just say you want to actually constrain space around the farm. Would you constrain it within your farm or without your farm, and why?
So the question is not clear.
The question is not clear. Come in again.
Okay. Let's say you want to create a fire belt around your farm so that it doesn't get gutted by fire. Will you do it within the farm or outside the farm? And
It
why?
should be outside the
Outside the
farm.
farm. Okay, you are
Outside the
wrong.
farm.
Okay, you are wrong, but you can talk about it. This is university, so it's an open mind. Okay, principle. We are all using open mind principles. Okay, here you can tell me whether you are right, but my answer, I'm saying you are wrong because you'll be cutting into someone else's farm. Y'all getting me right? If you actually create a
Yes.
space,
Yeah, we
Okay.
understand.
Yeah.
so you have to create it within. So when you create it within, we have what we call the inner buffer. So when you create it outside, you call that outer buffer. So for polygons, we have two ways of buffering around the polygon. In other words, we have point buffer, line buffer, polygonal buffer. Point buffers give us circles or circular polygons. Another name for a circle is a circular polygon. And then line buffers give us polygons, okay, depending on how it is cut at the end. And the polygonal buffers will give us another polygon. But then we can have an inner buffer for the polygonal buffer or an outer buffer for the polygonal one. Are you okay? So typically, everything that we just talked about, this is it. Are you okay? The distance that you use, for example, the radius of the circle is the buffer distance. It's called buffer distance. Yeah, so we always have a buffer distance, whether it's a polygon, a line, or a point. Okay, so you have the circular polygon as a result of the point buffer. Then we can have something looking like this for the line buffer. Okay. All right. So this is it. Then we can have the polygonal one. Where is it now? Okay. Okay. All right. So this thing was actually scrolling way down. Okay. So that's it. That's it. Why is it? Is this playing up? Okay. All right. Okay. So yeah. So polygonal buffer. So all the pictures you are seeing are describing the buffer regions with different colors. Are you okay?
Oh, okay.
Yes.
Okay.
So this is for a line up here, right? So we are buffering at different distances. Are you okay? Right. The first buffer is green. We buffer that again. We get yellow. Buffer here. We buffer the yellow. The final the output of a buffer is a polygon. So the polygon that we get, we buffer it again. That's what we are seeing here. Here is a polygon. We are buffering around it. It could be for security purposes. It could be for you can think about a lot of applications of buffering. Are you okay? Road construction, if you want to pull down some buildings, it's a buffer that is used. Are you okay? From the center line, you create a buffer and then you start, people are in trouble, isn't it? Your building has to come down. All right. So that is the concept of buffering, and I think we have 3 minutes. So let's ask questions. It's better to understand the lecture that you're actually going through than to just do a lot and not understand anything. So 3 minutes, you can ask a question. Otherwise, I think you probably end it as well. So yeah, this is the last concept I think so. Yes, I want to talk about. Initially, I thought it was the overlay, the layers, but I think we still have the buffer to also talk about. So any question on layering, the concept of layers, concept of buffering, the concept of topology? Can ask the next 2 minutes. The meeting will end and we can all say goodbye. The next topic, let me just talk about this. I think nobody has a question, so let me talk about this quickly. Let's appreciate coordinates. If you don't know coordinates, I think you're done basic land survey, so you know what coordinates are. They are just pairs, they are numbers. Are you okay? And then they define the location, the position of the thing. Are you okay? You know, in different dimensions. 2 dimensions are 2 numbers. 3 dimensions are 3 numbers. We talk about 4 dimensions. That's time. I want to know where the position of a thing at a particular point in time. Are you okay? All right. Coordinates are real. The coordinates that are used by surveyors can be really, they actually refer to an imaginary point, okay? But they're actually mathematical too. So we will talk about coordinates again. And the concept of distance is the Euclidean distance, okay? That most people know about. The distance between 2 points, a straight line, the shortest line between 2 is a straight line. And given 2 coordinates, you can always compute the distance between the 2. Okay. It's very important to know this. So yeah, that's the concept of coordinates. Okay. In our next lecture, we'll be talking about data acquisition. I will not even use a slide. Maybe I'll just talk to you and I'll show you a few pictures. But we need to know how we get data to put into the GIS. One of the ways to get data is surveying. One of the ways to get data is through photogrammetry. Drones, people are flying drones, and they are using it at weddings.
Yeah.
Can you imagine that? Okay, I'm okay with that. Are you okay? You never know. Maybe I may use it in my wedding. I'm still single. I'm not proud about it. I'm not proud about it. I'm still single. But it's like, seriously, I think we need to be looking at the scientific application too. Are you okay? Remote sensing is interesting, very, very interesting. There are satellites up there that are looking down on you. Are you okay? All right, guys. So we'll end it here and enjoy the rest of the week.
Okay, sir.
Now put the materials there.
All right, sir.
Take care.
Thank you, sir.
You're welcome.
Sir, yeah, sir, kindly give us the site for downloading. You made mention of downloading software.
Okay. I'll try and give you a link. Yeah.
Okay.
Okay. All right. Okay. Thank you very much.
Take care then. Bye.
So then, bye-bye.
Bye.
Sir, please, can we have a note now?